Welcome to Haxby Shed and part 9 of servicing this Harrison universal milling machine. Now this is the second of two videos where I rewire the inverters, the table switches, the speed controls, and I set up the interlock between the spindle and the table motors. It got a bit more complicated this time, but I think you'll find it useful. Now at the end of this video I've just tagged on a response to a very helpful comment that I got on my previous video. And then finally, before we kick off, I just want to say, about 5 weeks ago maybe, I posted a video on insulating our bedroom wall, and it's gone a bit crazy. So far we've had 39,000 views. We're picking up about 3,000 to 5,000 views a day at the moment, and 339 new subscribers. Now I hope some of those will stay when they realise that most of what I do is in here in the hobby machine shop. But I do appreciate it, so thanks very much. That was the operating switch for the table motor. But I don't want to disconnect it until I've got this inverter out, got it on the floor, and just see how it's wired. That'll be the next step. I've got the terminal cover off, just a bit of phone video. And you can see it's really old school. So you've got the dip switches there for various configurations, and then you've got 6 pots, again for various settings. I don't see an earth on this. I see live and neutral coming into the left. Maybe it just gets earth from the case, I don't know. Anyway, I need to look at the manual. I might have to work with it inside because it looks a bit difficult to get it off the case of the machine. These are the functions for those pots. I haven't quite worked it out except for the two on the right, number 5 and 6, look like upslope and downslope. In other words, how quickly the motor speeds up and how quickly it slows down when you turn it off. Another 3 hours gone. So what I've done this morning is I've put this new braided cable in to power the table motor. I couldn't get this out easily. This inverter case, apparently you have to put a screwdriver in from one side to unclip it. And I really didn't want to be doing that. So I was working with it kind of with my head upside down and using a mirror to see what I was doing. Total pain. Anyway, I've got this cable wired up to the motor now, so we'll just check the motor. It's still on the front panel switch as before. Well, now I've got the power side of that table motor inverter wired up, and we've seen the motor working. I've got to start on the 24 volt control side. Now when I looked at that inverter, I thought to myself, there's not enough wires on it. And in fact what they'd done is they'd left the 3-phase changeover switch in circuit between the inverter and the motor. Now as far as I know, you're not supposed to do that. All of the controls should be on the 24 volt side. Anyway, I need to start on that now, but I need to consider there should be an interlock between the spindle and the table motor. A friend of mine's got one, and he tells me the table motor will only run if the spindle's energized, turning. And that makes sure that you can't drive the table and the work into a static spindle. So I'm going to figure this out, and I'll tell you what I've done afterwards, because it's quite complicated and I still don't know exactly how I'm going to do it. So see you in a bit. Look at all that stuff on the floor. Take a guess how it went. It's taken me many hours to get this wired exactly as I want, but now it's all fine. So I'll explain to you in a diagram first what I've done, and then we'll come back and look at the physical. One complication of this wiring is we need an interlock between the table motor and the spindle motor. You don't want the table motor to run unless the spindle motor's running. So if you had a couple of modern inverters, you would wire it up like this. Now this bit here is just this bit I've shown you before. Okay? Now I've taken off the speed control from this diagram because it just complicates things. This is just the run, stop, forward, reverse. Now, modern inverters will typically have a 0-volt relay, and you can program that relay for something like 10 different functions, but one of those functions can be run. In other words, it makes the contact when this inverter is running. In any other condition, there's no contact. So what you can do is you take the 24 volts from the table inverter, it would be in this case, and you run it through here, it comes back and it runs through this relay, and then it only provides the run voltage to your forward reverse switch on this table inverter motor if this inverter is already running and this relay is closed. Pretty simple, isn't it? But where it gets complicated is when these two inverters are old and the wiring has to change quite a bit. By the way, thanks to Eddie for help with this relay part here. He put me onto something and allowed me to solve it. Now this is how I've actually wired the control side of these inverters. This inverter, which is an IMO Jaguar Cub, previous generation, has the relay, but the relay is only programmable on two functions, alarm and normal. Now normal can be run, ready to run, anything I'm feeling good about. It doesn't tell you for sure that this motor attached to this inverter is actually running. And the second complication is that on the Eurotherm there isn't a forward connection and a reverse connection. There's actually only a forward reverse connection. So if you put 24 volts on there, I think it runs forward. You take the 24 volts off, it runs in reverse. It's only on one line. So it's making the interlock quite difficult. But this part down here is what you saw before, pretty much. Now we've had to add bits to it to get the interlock to work properly. So everything to do with the table motor is in red and everything to do with the spindle motor is in blue. If I put all the colours on there, it'd just drive you crazy. Okay, so this bit, I'll take it you understand. Now, to do the interlock then. We're coming out here from the table inverter on plus 24, running through the switch, stop switch. Now what I've done here is piggybacked another relay onto this relay. So only when this is running will that relay close, and it will pass on 24 volts here to this forward reverse switch, which I've repurposed. So we've already repurposed the forward reverse switch, the three-phase switch, to give us forward reverse here on one gang, if you want to call it that. I'm using a second gang on it so that this connection is only made in the on positions, because when we look at those switches you'll see they've actually got 4 positions. So forward, off, reverse, off. So we've got to make sure that when this switch is in its off positions, the 2 off positions, 24 volts is not passing through to this table motor inverter. So from there, assuming this is made, we're in forward or reverse on the main motor. We come to the table safety switch, which is pretty obvious. Then we run across the relay, and what I've done there is wired it so that that relay will open if this inverter's alarmed. Coming back up here, now we come to the forward reverse switch for the table. Now the problem here is that because this inverter doesn't have a separate input for forward and reverse, it's combined, I would have a position here where it was forward in one of the 4 positions and it would reverse in 3 others. So on that switch I'm talking about. So what we've got to do is we've got to run through another gang on here, so it's always providing 24 volts to run this Eurotherm table inverter only when that connection's made. Do you get it? Easy as that. Took me a long time, of course. Let's look at the inverter for the spindle motor first. So, this is the new screen cable going off to the motor. This is the control cable coming in from the table. green, yellow, blue, speed control. Brown is 0 volts common, red is 24 volts out. These two here, grey and white, they're forward and the reverse, coming from the reverser switch. And then the pink and the black actually are in the loop, providing supply to the table inverter. So if this inverter alarms, it breaks that connection, and that means the table inverter can't run. Now the whole point of that is, you see, you could be commanding this inverter to run. It's got a positive 24 input, telling it to run on forward and reverse. So if you were relied on that only, you could actually have an alarm state. Without this, you could have an alarm state. The table motor thinks this is running, but it isn't. So you've got to loop that alarm relay in. This is the main motor reverser switch. So we're coming from the table switch, 24 volts positive run command, down to here, which is E, I think. And then we're leaving for forward and reverse on A and B. Now, in the bottom gang, I'm just going to call it the gang, down here, the blue and the red, they're the interlock for the table switch, to make sure that when this switch is in an off position, one of the two off positions, the table motor can't run. So that's across these two, which I think are F and C. Yes, F and C. Now you can see I've been labelling all this stuff because I can follow it right now, but give it 3 months, I wouldn't have the faintest idea what any of this stuff is. So I've spent an hour or more just doing labels. Whilst we're in the base, can you see I've labelled up all those connections as well. Now there was a real gotcha on that inverter, and it was to do with the cover. Now that cover very helpfully tells you what all the potentiometers do and all the connections do. But what it doesn't tell you is this label's on upside down. It says power, status, health on these 3 LEDs there. Now the right hand side one, of course, is health. Turn it over, the right hand side one is power. Well, I think this is all self-evident really. Does it need any explanation? Took me quite a while, and it was a bit of a so-and-so. But anyway, the two relays are tucked in there, look. They're just silicon to the side of this plate. And I have used neutral silicon. It's not acid cure silicon, so it shouldn't dissolve the wiring. Sort of gotchas I had in here, well, one was, for some reason, this start switch for the table wouldn't connect. So physically it looked like it was connected. It must have been slightly corroded. Another gotcha was, with all of this backwards and forwards needed for the interlock, I run out of connections on this one, on the table, control 8-core cable screened, so I had to use one that was a spare in this one here. Those are the rotary speed control switches, so I need to mount those on the side here, up here, but otherwise, you know, you're probably better looking at the circuit diagram than looking at this bird's nest. But it does all work. Next steps are attach these two back here with a couple of P-clips, because obviously this is earthed braid and it could short something out, so we need that well out of the way. Make a couple of holes in the side of this case to put those speed potentiometers in. And then down below, where the main screw comes down from here, I'm a bit worried that this might get hold of some of the cables, so I'm going to put this in a tube below, piece of sink waste pipe or something like that, maybe standing on its own base. I've drilled 2 7mm holes for the speed control pots. I'm going to use this. It's a bit unusual, but I do like it. And then I've got a counterbore here, which started life as an 8mm counterbore. In other words, that bit was 9mm actually. And I've ground it down, because I have a spare. It had been ground here anyway, which kind of ruined it. And with a bit of luck, that will go in there, and I can just counterbore this because it's a bit too thick for getting those screws onto the end of those pots. Try not to go right through it. You know, this is going surprisingly well. No clue what I was saying here. We could run a caption competition, couldn't we? I can start the spindle from here now and I can control the speed. Hopefully you can hear that running. So here's the table motor, and I've put a piece of paper on the top so you'll see it spin hopefully. So start the main spindle. It's not spinning because I haven't got any belts on. Start the table motor. Press the trip. Press again to start it. Reverse the main spindle. You can't see what I'm doing, but I'm just reversing it honestly. Press start again. What else am I missing? Oh, I can reverse the table motor. I hope. Oh, I have to press start again. There we are. And then I can adjust the speed of the table motor. It's on a long slope, so it takes a little while. And then up. I need to adjust that really, and I want to adjust the speed range as well. That's far too high. Goes up to 120 hertz, I think. More than double speed, I think. And then I stop it, then everything stops. Just a few more things worth saying about this inverter setup. If we look at the Eurotherm inverter, not this blue one, but the one that's in the base that drives the table, it already includes circuitry for momentary switching. We don't have to provide an external latch relay. And if we put plus 24 onto pin 3 through a normally closed stop switch, and we put a pulse onto pin 2 through a normally open start switch, then when we press this button the thing will start. When we press this one it'll stop. That's fine. However, if you don't have this line here and you constantly power this, the inverter will run. So you need to be really careful where you pick this point off. So in my case, where I've got multiple interlock switches, you've got to make sure that you're picking off at the very last one at this point before it comes into this terminal here. If I was to pick this up much further back, this might be 0 volts here, but if I'm picking up a positive much further back somewhere in the interlocking chain, when I press that button this inverter would start. It wouldn't stay on when I release, it wouldn't stay on, but it would run and it would drive the table motor anytime I'd got that pressed. So that's a bit, you know, of it where you need to apply a bit of care. The other thing that I'm just going to talk about, if you remember, I said that Eurotherm didn't have a ground connection. It was just live and neutral from the main supply. Well, in fact, it doesn't require a ground connection, but it does mean that it floats. In any case, you know, both of these inverters give a 24 volt output, but they're not referenced to each other, so you've got to keep them completely separate. So here, just there, we've got plus 24 coming in from this blue inverter, and over here, one of these two anyway, I think it's this red one perhaps, we've got plus 24 coming in from the Eurotherm. Now those have to be kept separate. Well, the 24 volt line for this inverter, the cub, is giving about 36 to ground, so that is floating. And if we try the Eurotherm inverter, well, that's giving what, 45 to ground. And then if I compare the two, there's about 8.2 between them. So it just illustrates you've really got to keep those two 24 volt circuits separate. They might be called 24 volts, but they're floating all over the place. Let's put this tube on, shall we, onto this screw. I've just screwed the knee up as far as I dare. You could do some close work there. Here we have one piece of waste pipe. Oh, excuse me. That table's all the way down now, and that's fine. I'm just setting up this motor speed range on the table inverter. It's very difficult to read. 1487 that says, 1382. Well, it's a 1340 RPM motor when it's running on 50 Hz, and I've set it so that it'll run up to 61 Hz and down to 41 Hz. So that gives me a range of about 1100 up to about 1650 RPM. So that's all I need really on this, because the range on the gearbox is 14 to 1, so the slowest speed to the highest speed is a 14 times ratio. So all I would expect to do with this is, if I'm doing a cut and it starts to vibrate, I could just slow the table down a bit or speed it up a bit, you know, with a maximum sort of 2 to 1 range on this. And if the gearbox has got 14 to 1, you can see it's only small in proportion. So I'm quite happy with that. Well, here's a bit of unwelcome news. Just as I've got everything finished and I'm pretty much ready to put that front cover on, the inverter and main motor start playing up. When I try and start the main motor, it throws up an overcurrent. It starts to spin the motor, so it's a problem on acceleration, but then it just gives me the overcurrent code. I've tried everything. I was adjusting the parameters slightly, but only to set the speed range, that's all for that pot. Anyway, you know, 2 hours into this so far, and I just wanted to try another 3-phase motor, so I've just put on that welding positioner motor. It's only 60 watts. It kind of proves that the inverter's working okay, and I can adjust the speed, so I'm kind of getting stuck. It does look like the main motor, but I've checked between the windings, I've checked the connections, I've checked for, you know, any kind of copper whiskers that I've left anywhere. Not what I wanted to be saying at this stage. Assuming that we've got a problem with the motor, I disconnected the leads and separated all the windings. So across A, 3.9 ohms, 3.9 ohms for B, same for C. That looks all right. So I tested the insulation resistance at 1000 volts, and C to ground is 440 megs, B 390 megs, A 320 megs, and then between the coils, A to C 420, A to B 360, and C to B 440. So all that looks good. Now, when I first had this problem, the motor would only spin up to about 8 or 10 Hertz before it tripped. But by reducing the torque boost, I can now get it to run to about 20 Hertz before it trips. So that gives me a bit more time, and I'm going to put this meter on each of the loops and see what they draw. So I've put the clamp ammeter across one of the phases. We'll start the motor and we'll see what current we get before it trips. A bit hard to tell for me, looked like about 20 amps. Now this motor is supposed to draw 5.7 amps per phase, and that implies to me that the voltage is too high, because the inverter controls the voltage on the terminals. If you're running at 25 Hz, then maybe you'd be at 120 volts. If it was linear, 240 volts at 50 Hz. There's something strange about this. It's beginning to look like an inverter parameter again, but honestly, I don't know. I tell you what, we'll measure the voltage across the terminals if we can. Well, my auto ranging meter didn't like that. Now, it's not a sine wave anyway, so we won't get a true reading, but we should get something. Take 2. 179 volts before it trips. Now you can see on the screen there that its target frequency is 25.7 Hz, so about half speed for that motor, but I've extended the acceleration time to over 20 seconds, so let's see what happens then. Still running, still running, still running. 20 Hz. It trips at 20 Hz every time. If I extend the acceleration time, it still trips at 20 Hz. So that suggests to me that the voltage versus RPM curve is wrong, and it probably is a setting, and it's probably my fault. So I think what I'm going to do is I'm going to do a full reset on this. So to reset all the parameters to factory default, you have to go to HS176 and make that 1 and save it. So we have to scroll through to H, let's go this way, there we go, HS176, set, I have to press stop and up together, there we go, save it, it should reset all the parameters now. So this will be controlled from here now, fine. Now I need to put in the motor current because the default is too low. F11. I hope this is useful to somebody because it's just darned annoying to me. Oh, well that's strange. Anyway, well, I don't know why that was 6.1 because on the sheet, I don't know. So that must have been the default then. And it was running like that before, so that's not going to change anything. So let's see if it runs. Oh, goodness knows. Right, start, run. Oh my goodness, some parameter was not right, or something got stuck. Like I said, I hope it was useful to somebody. Now to get this to work from the buttons on the table, instead of these two here, I had to set FO2 to 1, and now to get the external variable control speed working from the table, I have to set FO1 to 1. So press this. Let's go down 1 to FO1, do this, set it to 1, save it, go to start the spindle, adjust the speed, which I'm doing from the table now, and stop it. Now it's all working again. I'm going to check the current on one of the phases. It will never show 5.7 amps, which is the rating on the plate, because this is not measuring a sine wave. It's set to run up to 50 Hz, so full speed. Ta-da! I've set the speed control to range between 35 Hz and 65 Hz. Now, if I select top speed on the gearbox, 65 Hz gives me 1950 RPM, near enough 2000, and some of these machines ran at 2000 anyway, and 35 Hz gives me 1050. Now, what I've tried to do is basically the same as I've done on my lathe, which is to have a speed range which was equal to the spacing on the gearbox. So the next speed down from 1500 on the gearbox is 958, and 35 Hz will give me 1050, and the span in different places on the gearbox is different anyway. I think that's a reasonable policy. That's my policy. Now that meter was reading double because it's picking up on both of these dogs here, but it was saying 3000. I've got the inverter set to 50 Hz, it's 1500 on the box, so that all ties in. Now I've rewired the control side of the inverters. We've got a couple of holes in the front panel which will take these 22mm LEDs. This green one I'll use to indicate mains supply, and this amber one I'm going to use to indicate an alarm on the main motor inverter. If you can look at this diagram, we've got the Eurotherm inverter that drives the table, and that routes through a relay on the cub inverter that drives the main motor. And I can use this relay, this will trip over when this cub alarms, I can use this relay to switch a lamp, this amber LED, and drive it from the 24 volts which is coming off the Eurotherm. But the thing is, the Eurotherm 24 volts can only supply 20 milliamps, and each of these inputs here takes 5 milliamps, so for run, start and direction. So I've only got a budget of 5 milliamps to drive this lamp. So we need to measure the current that this is taking, And if it's over 5, maybe with a bit of margin as well, then we need to do something about that. But the other thing I need to do as well is I need to check what current is actually drawn on this line here, because although, you know, 3 5s are 15, should give me 5 left, if these are drawing more, I'm going to have less than 5 to drive this. So, you know, great theory, but we need to test it in real life. So let's check the current that this is drawing. I've got a 24 volt supply, 5.9 milliamps, so we're a bit over budget there. This is the idea, look. I think those will look smart. So the alarm one will go this side. I can pick up at any point in the plus 24 circuit, so I may as well do it just there. Okay, that's the current load with the run only. If I press start, that takes it up to over 10. And what I've discovered is when the table motor's set to running one direction, there's no current draw on that control line. But when I set the table motor to run in the other direction, because of just the way that works, it's going to give me a draw, which is there, 15.9, look. So we only have about 4 milliamps left on the budget. That's a pain. I don't know if the LED is going to run at that. I thought I'd better check the current budget on the Cub 24 volt line. And the budget is 40 milliamps. Now that's just driving 2 latching relay coils at 15 milliamps each, and then either forward or reverse. So 2 15s are 30 plus 5 is 35. So at least in theory we're okay with the budget on this line on the Cub. So the task now is to see if we can reduce the current through this LED down from 5.8 milliamps to 4 milliamps. Now it's a bit tricky. LEDs are non-linear. This has got some kind of driver in it, I know, because I can connect it up either way, positive, negative, and it still works. But anyway, let's give it a go. 24 volts divided by 5.8 milliamps means the effective resistance of this is 4.14k. If we only want 4 milliamps to come down here, 24 volts divided by 4 milliamps is 6k. So the difference is 1.86k, and that's the value of that resistor. Now resistors don't come normally as 1.86k, they work in preferred values. The nearest preferred value would be 1.8k, and I fumbled through my box of bits and I found one. Let's measure it. 1.797k. Well, that's near enough for Haxby Shed. I don't know if you're familiar with the resistor colour code, but each resistor has 3 coloured bands here to give the value and 1 here to give the tolerance. So this coloured band is the first value, this is the second value, and this is the number of tens multiplier. And the colours run from black, which is 0, to white, which is 9. So what we need is this one. That's probably too far away for you to see, but it's brown, grey, red, and that's 1.8 k ohms. I think we're going to be lucky. I don't know why this meter's got a bias of 0.7 milliamps, but it's just what it is. So that's drawing 4 milliamps, and can you see the LED is on? It's not so bright, but it's good enough. That's the green mains LED wired in. If you have an LED on its own with nothing else, when it triggers, it short circuits and would burn itself out. So just an LED on its own needs some kind of limiting resistor with it. But it was pretty safe to assume that these had the resistors in, and in fact, as I said, they do seem to have a driver in. Just testing. Whoa! So here we've got the relay. Well, I'm pointing to this, I think it must be the relay, and here are the contacts. So 30C is common, 30B is normally closed, 30A is normally open. if this alarms, the relay pulls over, so we get from common to this one, the yellow one, and the yellow one goes off to that light that I've just put in. Then the other side of it, which happens to be this pink here, goes off to the 24 volt common rail on the Eurotherm. Well, it's together, but how do I test it? When I was having problems with that inverter, it was alarming all the time, and I was able to prove that the interlock with the table motor works. But how do I get it to alarm now? I'm going to run it on full speed and see if that will alarm it. It usually does. I think the oil in this gearbox, you know, is too thick. Well, that was much quicker than I expected. Right, I can't cancel the alarm from here. I have to turn the machine off. But it works. Brilliant. But the oil in that gearbox, you know, is too thick. We'll just try it on the low range. Well, just proving the obvious really there. The comment came from Sean. I think he's in South Africa. I hope I got that right. And his comment was about the protection across the relays that I'd used. So here's my little drawing. 24 volts across the coil, creates an electromagnet and opens or closes these contacts here. Now you probably all know that, you know, that's how an electromagnet works, but you may not know that when you disconnect the supply to that coil, the magnetic field collapses and induces a voltage which is large and in the opposite direction. So I got this diagram from the Panasonic website, and you can see this huge spike that occurs when you disconnect the coil. It operates on just the same principle as the old car ignition coils. So, to protect your electronic equipment connected on that circuit, put the diode across the inductive load, which is the coil in this case, and it clamps that reverse voltage, because a diode is like a one-way valve. It allows current to flow in one direction. It won't allow it to flow when the voltage is reversed in the opposite direction. And we use that to basically suppress or clamp that reverse spike. And that cleans up the waveform, and it stops 260 volts in this case, you know, flying down the line on the 24 volt circuit supply in the inverter. Now I looked at the new inverters that I've got, and they all seem to have that protection built in. But on the inverter in the base of the milling machine there, which is an older generation, it says in the handbook to always apply the diode across the coil of a relay. Diodes are not very large, they're extremely cheap. I think I'm getting about 10 for about £1.50, so you know, $1.70, something like that, maybe $2 US. They're about the size of a small resistor. But that little device, which hasn't arrived yet, when it does I'll fit it, you know, is likely to save my inverter. So thanks very much for that, Sean. Hey, the diodes have just arrived. I said they were small, look. You can size them against that threepenny bit. I hope you remember threepenny bits. They were currency before 1971 in the UK. Back in here again to fit the protection diode between these two blues here. They're the loops between the coils of the two relays. Now, I should have made them different colours, didn't think of that, but I'll use my meter to test. I think I could put that relay anywhere in the base, between the plus 24 and the 0 volts, but it's probably best to have it close to the relays. So if we test this diode, you see that silver line, put the negative at that side, and you see it conducts. If I turn it round, it doesn't conduct. I've put that connector block in to hold the diode. The right hand side wire is positive. The negative side of the diode goes to the positive, and then when you get that reverse spike from the coil, the diode will clamp it. I've also labelled it, and I'm going to label it protection diode. I'm going to pot it in the white silicon, which I had for the windows, which is non-acid curing, so there will be no acid to attack the wires. I've been warned about that many times, folks. Well, that was a long job, wasn't it? I really could have done without that twist at the end. I've no idea why that inverter played up like that. The parameters that I set, again, after I'd done the reset, were just the same ones. So whether there was a hidden parameter or something, who knows? Bit noisy, isn't it? I hope that was useful to somebody. Thanks for watching Haxby Shed.